Assalamualaikum warahmatullahi wabarakatuh. We are from group 2. We will present about experiment 8, heat transfer coefficient in Dropwise and film condensation. This is our group members, myself Nurul Afifah, Muhammad Azhan and Umar Irfan. Introduction. For this experiment, condensation can occur in two main forms, dropwise and film condensation. Dropwise condensation involves stationary liquid droplets accumulating on a surface, which is efficient for heat transfer under specific conditions. Film condensation, on the other hand, further a continuous vapor layer on the surface that flows downward, offering more predictable and efficient heat transfer. Film condensation is commonly used in industrial applications like vapor power cycles to enhance condenser efficiency, while dropwise condensation is less commonly employed due to its inconsistency and difficulty to maintain in industrial machinery. This is the formula that related to heat transfer coefficient is as follows. Alpha equal to transfer thermal power divided by condenser surface area multiplied by temperature difference between the saturated vapor and the wall of condenser. And this is the apparatus that we use in this experiment. For this experiment, it has only one objective, which is to determine the heat transfer coefficient for the dropwise and film condensation using the condensation process demonstration unit. Scope for this objective: compare the condensation process between two different materials. Next, compare the size of bubble produced when increasing the volumetric flow rate. Evaluate the heat transfer coefficient in dropwise and film condensation with different volumetric flow rate. Next, theory. Film and dropwise condensation are two modes of the condensation process that occur when vapor turns into liquid on a solid surface. This diagram shows that film-wise condensation and dropwise condensation react. For film-wise condensation, in film-wise condensation, a continuous liquid film forms and flows down the surface. This mode is more common, provides good heat transfer, and is easier to achieve the practical system. And dropwise condensation is less common but more efficient. In this mode, discrete liquid droplets form on the surface, providing higher heat transfer rates. However, it can be challenging to maintain in real systems. The choice between these modes depends on factors like the fluid, surface properties, and application, impacting the efficiency and design of heat exchanger and condensers. In this video, we can see that a vapor layer on the surface flow downward in different material. Next, we can see the apparatus. This is the apparatus that we use in this experiment, which is heat transfer coefficient in dropwise and film condensation. The left side is the flow rate valve button, and the right side is the data that we need to record in the table.
Now, I will talk about methodology that we use in this experiment. Step 1. The power switch is turned on to run the apparatus.
Step 2. The water source is open. Step 3. Rotate the heater power and switch on. Step 4. Record the initial reading into the table. Step 5. Wait for 10 minutes to let the system to stabilize. Step 6. Adjust the cooling water flow rates V1 and V2. Step 7. Increase the cooling water flow rate, which is to 2 liter per hour plus minus by turning the valve anti-clockwise. Step 8. All values T1 until T7 are recorded into the table. Step 9. Step 6 until step 9 is repeated by increasing the inlet water flow rate consistently. T1 until T7 are recorded into the table. Step 10. Heater power. Main switch, water source, and power switch are turned off after the experiment. Step 10. Heater power. Main switch, water source, and power switch are turned off after.
So, we continue with the result and discussion. This is all the data that related to the condenser, which is diameter, length, surface area, surface quality, density of water, and specific heat capacity of water. This is the table for the film condensation. The table shows all the recorded data that we get from the experiment. In this experiment, we manipulated the volumetric flow rate, which is from 0 to 8. In this table, we have to calculate the mass flow rate, thermal heat transfer, and coefficient of heat transfer with using the formula given. Under the table is an example of the calculation for 2 liter per hour volumetric flow rate. The formula for mass flow rate is M equal to rho V, and we get the answer is 5.556 times 10 to the power of negative 4. For thermal heat transfer, the formula is Q equal to M Cp delta T. The delta T refer to the outlet temperature minus inlet temperature. From this formula, we get the thermal heat transfer is 1.163 joule per second. To calculate the coefficient of heat transfer, we use the formula alpha equal to Q divided by surface area times delta T, which is the delta T is referred to steam temperature minus surface temperature. From this formula, we get the answer for coefficient of heat transfer is 56.876 work per meter square. Okay, this is the table for the Dropwise condensation. The table shows all the recorded data that we get from the experiment. For the mass flow rate, thermal heat transfer, and coefficient of heat transfer, we have to calculate using the formula given like the slide before. On this experiment, we plot the graph coefficient of heat transfer versus volumetric flow rate. On the left is the graph for the film condensation, and on the right is for the Dropwise condensation. Both graph is an increasing graph. Between the two graphs stated, we can see that the Dropwise condensation is more effective than the film condensation. On this slide show the comparison between small bubble and large bubble when we increase the volumetric flow rate. Without any delay, we continue with the discussion. Number 1. Shape of the graph obtained and related to the ideal gas law, which is Charles law. According to the shape of the graph obtained, which is the graph heat transfer coefficient versus volumetric flow rate in film and Dropwise condensation, the graph shows the increasing graph in both. We can conclude that the heat transfer coefficient increase when volumetric increase. The relationship between the volume and temperature of a given amount of gas at constant pressure is known as Charles law. Charles law states that the volume of an ideal gas is directly proportional to the absolute temperature at constant pressure. Mathematically, Charles law can be written as V proportional to T, or V equal to constant T, or V equal to KT, or V1 per T1 equal to V2 per T2, with K being a proportionally constant that depends on the amount and pressure of the gas. In other observation in this experiment, the size of bubble is increasing when the temperature increase. It is an intuitive idea that bubble of air will expand if you heat them, as long as the pressure remain constant. It is also fundamental component of the ideal gas law, first written down in the early 19th century by the French natural philosopher Joseph Louis Gay-Lussac. Number 2. The effectiveness of heat transfer coefficient in film and dropwise condensation. Based on the plot graph we obtained in film and dropwise condensation, we can see that in dropwise condensation, the heat transfer coefficient is higher than in film condensation. This is because in dropwise, discrete liquid droplets form on the surface and providing higher heat transfer rates, while in film, a continuous liquid film form and flow down the surface. The picture shows that the condensation process happen in film-wise condensation and dropwise condensation. Lastly, we can conclude that in this experiment, the condensation process in dropwise is more effective than in film condensation.
So I will present about the conclusion for the experiment. So for the conclusion, this experiment shown the condensation that happens in the film condensation and dropwise condensation. In this experiment, we can see that dropwise condensation is more effective than film condensation. Furthermore, the heat transfer contact between vapor and surface in dropwise condensation has better than film condensation. Even though the dropwise condensation is much better than film condensation, but industrial fields are often used film condensation due to it is more reliable. So next, I will present about the safety procedure. First, wear a neat clothes before starting the experiment, especially lab coat. Second, before start the experiment, make sure that water level is enough in the tank. Third, make sure your hands are dry before pressing the switch button. Fourth, make sure the water is always flowing to avoid interruption during the experiment. Fifth, do not touch the tank during the experiment to avoid hand injury. And lastly, sixth, turn the valve slowly to get an accurate reading. So lastly, I'm going to talk about the reference that we use in this experiment. So this is all of the reference that we use to run this experiment. I think that's all from our group. Thank you.